Hello and welcome back. We talked in our last video about how we could relate cell potential to delta G, and we got the equation that delta G was minus NF times E cell, all at standard conditions. And so we said, hey, look, we can calculate delta G naught there by using our cell potential. But we also know this relationship that delta G is equal to minus RT times the natural log of K, right? And I'm going to put KQ here just so we're very specific about what we're talking about. So we have these two different relationships for delta G. And just like in math, if A is equal to B and B equals C, then A equals C. And we can set those equal to each other. Minus NF E cell is equal to minus RT times the natural log of KEQ. And most people will rearrange this and they'll solve for E cell, which just says it is minus RT over NF times the natural log of KEQ. Now that's easy enough to calculate. We know the values of R. Which one would we use in this case? Hopefully you got the 8.314 joules per Kelvin mole because we're talking about energy related things. Times temperature divided by N, right? That's the number of electrons in your balanced overall reaction. And Faraday's constant times the natural log of KEQ. For historical reasons, it used to be difficult to calculate logs and things like that and put, even just regular numbers. And so in the past, more people were familiar with log tables than natural log tables. And if you're wondering what a log table is, back in the day when there weren't calculators, how you calculated logs is there were some heuristics you used, and then you look up the log in a table of logs. I once had I think it was a 1918 copy of the the CRC math tables. And the thing was in pristine condition except for the log tables. Every page was beautiful, 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 beautiful. But then when you turn to the log tables, they were oily, they were greasy, they were taped together, because that is what a chemist might have been using primarily is, hey, how do I find the log of this? Of course, now we have calculators to do it for us, and so it's not a problem to use this form of the equation. But for historical reasons, people said, hey, look, if we're talking R, if we're talking T is room temperature, if we're talking Faraday's constant, we can just calculate all those things ahead of time. We can also change the natural log to a regular log. You can look up how you do that. We don't need to know it for this thing. But what you get is something that looks like this. 0.0592 over N times the log, this is the regular log base 10 of KEQ. And that's our E cell. And this is a very common way of calculating cell potentials, or calculating Ks from cell potentials. So we'll do an example real quick, and we'll say, what is K for the nitric acid copper cell? Now, this was one we did as an example in a couple videos ago, so I'm just going to tell you the answer that we figured out that E cell was 0.44 volts. So not a huge voltage, right? 0.44 volts, that's not very large. And so we're going to get that 0.44 volts equals 0.0592 over N. N in this case was 3 times the log base 10 of K. Right, multiply both sides by 3, divide both sides by 0.0592, and you get that the log base 10 of K is equal to 22.30. And so K is equal to 10 to the 22.30, or 2.0 times 10 to the 22nd. Well, it's a very, 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 very large K. Those are the kind of Ks we were talking about when we were talking about complex ion formation constants, things that are extraordinarily favorable. And so that's what we find about these redox reactions. They are extraordinarily favorable. The reason your battery runs is because it really, really wants to. It really, really has energetic reasons for making the products of your battery and also all that energy. So that's one thing to keep in mind about these electrochemical reactions. They essentially run to completion. So you run out of something. Now, what we'll find going on is that as you start to run out of things, it can and will change the voltage of your battery and change that driving force. But for now, just look at this number and be like, okay, wow, that is something that really wants to drive to completion. All right, so our next thing says, hey, look, if we can relate something to K, our equilibrium constant, we can also relate it to Q, which was, remember, the equilibrium constant, the same form of it, but when we didn't know, or we were certain, that it was not at equilibrium. And so we had this expression, delta G equals delta G naught plus RT natural log of Q. And it turns out that even though we had been using the minus NF Ecell naught here for our delta G naught, there was nothing in our derivation that limited that to standard conditions. And so for non-standard conditions, we can put that there. The delta G is minus NF Ecell without the little zero. Because remember, all that little zero, all that little thing superscript says is standard conditions. 1 molar, 1 atmosphere, 25 degrees Celsius. Plus RT natural log of Q. Most people will end up dividing this thing by the minus NF to get that Ecell equals Ecell naught minus RT over NF times the natural log of Q. And just for the same historical reasons, in the past, people have generally written it like this. If you're talking about 25 degrees Celsius, 0.0592 over n times the log 10 of Q. And this is what we call the Nernst equation. And it is a great way of calculating cell potentials at non-standard conditions. So we can look up Ecell naught, right? We know how to do that now. We know how to look that up in those tables, right? The thing that's higher on the standard reduction potential is going to get reduced. The thing lower is going to get oxidized. Cathode minus anode, we can get Ecell naught. Q, how do we calculate Q? Well, if you remember, if you have a reaction, right, A goes to B, or you have C's and D's or whatever, right, Q just has the same form as K. It's going to be the concentration of A to the A, the concentration of B to the B, etc. Oop, I did reactants over products. Products over reactants, B to the B, A to the A. Right, okay, so there we go. Products over reactants, exact same form as K, but here we don't know if it's at equilibrium. So, excuse me, that is what we're going to do. So let's go ahead and do a quick example on that one. We're going to do that nitric acid, copper cell that we did before. Now, the difficulty here is that we now need to know everything, right? We need to know N. N comes from the balanced reaction, but we can usually get that by looking at the two half reactions, being like, hey, let's just make sure those N's are balanced. But Q, right, we have to know the coefficient of every single thing in our balanced reaction in order to do Q. Like I said, the lovely thing is those tables of standard reduction potentials have already done the half cell balancing for you. So you don't have to do the half cell balancing all on your own. That's a wonderful, wonderful thing. So if you remember, we had our Cu plus 2 plus 2E minus going to Cu solid, and we had our NO3 minus plus E minus hold on, I think there's a little mistake in my notes, and I just need to double check what that is. Yes, because it was going to Cu plus. There we go, Cu plus. And then we're going to go ahead and say we've got our NO3 plus 4H plus E3 minus goes to NO plus 2H2O. There we go. There's our two half reactions. We already figured out our cell potential for that one. Our cell potential was 0.44 volts. We used that in the last example. And that's under standard conditions. But what we're going to do is we're going to make some non-standard conditions. We're going to change the copper concentration, Cu plus, is going to become 0.010 molar. All others standard. Okay, so we're not going to change any other concentrations. They're going to be 1 molar or 1 atmosphere of pressure. And we want to go ahead and figure out our Q. How are we going to figure out our Q? Well, we need to write this as an overall balanced electrochemical reaction, which means we need to multiply this guy by 3. And was it reversing him or keeping him separate? This one, if you remember, was reversed. This is the one that was oxidized. This one was the one that was reduced. If you can't remember that, you can look up those cell potentials and remind yourself from a previous video. So what you end up with is a reaction that looks like this. 3 copper solids plus NO3 minus plus 4H plus goes to 3 Cu plus plus NO plus 2H2O liquid. And then we got to put our phases on here, excuse me, because it's important to have all those phases there. Why? Because we have to know how to write our Q. In order to write our Q, we need to know all the phases. Why? Because liquids don't generally appear in the Q. Solids don't generally appear in the Q. So we're going to write our Q here as products over reactants. It's going to be the concentration of Cu plus cubed times the partial pressure of NO divided by the concentration of NO3 minus times the concentration of H plus to the 4th. Now you'll notice our Q here looks a little weird because we've got a concentration multiplied by a pressure, and that's okay. Because when you have all these values in here, when you have these cell potentials, when you have these delta Gs, they were calculated using gaseous NO. And so gaseous NO is what needs to go into our equation for our Q, for our K. Even though this is what we call a mixed phase Q, a mixed phase K, it's okay. It's built in there. The calculations are already done with that mixed phase in. And if you remember at the very beginning, a long time ago, when we talked about these equilibrium constants, we said a couple things. One, for our purposes, we're going to divide everything by a reference. And so there's not actually any units on these things. So that helps out a lot. And right, if you have twice as much gas in molarity and you have twice as much gas in pressure, it's essentially the same thing, right? Twice as much gas will make twice as much gas pressure. Twice as much in solution will make twice as much in solution. So when you actually do these relative things, it all works out pretty well anyway. The second one is these equations are actually wrong anyway, because we aren't actually using concentrations and pressures. We're using what are called activity coefficients related to concentrations and pressures. But in reality, these are all just the activity coefficients of these things. But we're using this as a shorthand because it works pretty darn well for most circumstances. All right, there's an aside for you. So we have to calculate Q. Everything else was the same. The only thing we changed was our copper to 1 plus. And so we got 0.010 molar. Nope, no molar, right? We just talked about that. Cubed. Everybody else is 1 to the 4th because we decided to keep those as the same. And so our Q here is going to be 10 to the minus 6 because we had 10 to the minus 2 cubed. And so we can go ahead and put that into our equation. E cell equals E cell naught minus 0.0592 over n, the log base 10 of Q. And so we get E cell equals 0.44 volts minus 0.0592 over n. What was n in this case? Well, we had to multiply everything by 3. 3 electrons here, 3 electrons here. And so our n is 3 times the log of Q, which is 10 to the minus 6 here. And if you do all that work in your calculator, you get 0.56 volts. 0.56 volts. Now, you'll notice that's greater than our standard cell potential. So we've actually made a better battery. Why have we made a better battery? It's just Le Chatelier's principle. what did we do? We reduced the concentration of one of the products. What does Le Chatelier's principle tell us? The reaction is going to respond by making more product. Remember that 0.44 volts assumes you already have 1 molar in 1 atmosphere of all your products. How often do we start with all our products there? Right, we don't. We start with low amounts of products or 0 products, and so we should expect that our voltages will be going up. Okay, and this is related to how batteries, when they age, they change voltage. Because as you make more product, as you have more of that stuff there, the voltage is going to go down because your Q is going to make it so that you're subtracting off things from your E cell. All right. So that is how you calculate cell potentials at non-standard conditions. And I'm just going to remind you, these zeros and these not zeros, these standard conditions, these not standard conditions, they're very hard to grasp the first time you're learning all this stuff. So if you're struggling with how do I know when it's 0, how do I know when it's not this 0, you're not alone. It took me years and years and years and years to figure out this and be like, oh, that's actually not that hard. But it took me years and years and years and years and years and years to get there where I finally understood it. And I could do the mechanics, I could get the grade in the class, but like to really actually know what was going on took me a long time. So if you're struggling with that, don't worry about it. Work on the mechanics of it, right? Even if you don't quite understand the details of it, you're still okay. Oops, there we go. A check-in. We want to know what the cell potential is for this galvanic cell. Notice we're asking for E cell, not E cell not, right? That's a very tricky thing, right? If I just put a not there, then you'd actually be doing a different problem than if I didn't put it there. So be very, very careful and do the mechanics of knowing whether those little symbols are there or not. So there's this galvanic cell. We did this one before, but now I've changed the circumstances to say that my silver concentration is 0.05. My lead concentration is now 0.01, and I want to know what is the new cell potential under these circumstances. All right, and go. What did we come up with? First thing we need to do is figure out our standard cell potential. If you remember, this thing's higher up, so this is going to be reduced. This is going to be oxidized, and we got our E cell not is 0.91 minus a minus 0.13, and that was going to be a 1.04 volts. Now we have to figure out Q in order to do this, which means in order to figure out Q, we need to figure out our overall balanced reaction. We're going to have to multiply this guy by 2 so that we have 2 electrons on either side. Which one's going to get reversed, right? This one gets reversed, and so we have lead solid plus 2Ag plus aqueous goes to lead 2 plus aqueous plus 2 silver solid. Our Q, we don't include our solids in there, it's just going to be the lead 2 plus over the silver plus squared. Still a lot of people I see forgetting those coefficients, right? You got to put that squared there in our K's and our Q's. And so that's going to be 0.010 divided by 0.050 squared. And where did that go? Oops, where did that go? There you go. That is the number 4. I knew I had it somewhere. I just had to find it on the page. So we get E cell is equal to E cell naught, which was 1.04 volts, minus 0.0592 over N. What was N in this case? We look back up here. We had to multiply everything by 2, so each one of them had 2 electrons. So that's a 2 there, times the log of Q, which in this case was 4. You plug all that into your calculator, you should get the value 1.02 volts as your new cell potential, and we get the answer of D. All right, here's a funny one. A cell without a cell. Professor Clements, what are you talking about? What I'm going to do is I'm going to make a cell, and I'm just going to use copper. You're like, Professor Clements, no. You told us many, many slides ago that you can't just use copper because you'd have nothing to compare that copper to, nothing that copper wants to give up its electrons to or can take electrons from. You always need to have it referenced against something else. So you're going to run copper with the standard hydrogen electrode, aren't you, Professor Clements? Like, no, I'm actually just going to run copper against itself. And you'll see in just a moment why earlier I said, don't do that. And here I'm saying, let's try it. Okay, so I'm going to have two beakers here. I'm going to have my beaker on the left. I'm going to have my beaker on the right. It's going to have a copper electrode. This guy's going to have a copper electrode. We're going to connect those via wire up there. And we're also going to do our salt bridge. And we're going to make this a Cu2 plus, Cu2 plus. Now, if you looked at this and everybody was at standard conditions, what would you expect this cell potential to be? Well, you might be like, okay, well, I do cathode minus anode. I have no idea which is the cathode and which is the anode. But since they both have 0.34 volts, I can say the E cell naught is equal to 0.34 minus 0.34 is equal to 0. And I'd expect this cell to have 0 volts, which is not a very useful thing, Professor Clements. Why are you talking about this? And you'd be correct. Absolutely. This thing would have 0 volts. If you put the same thing on one side and the same thing on the other, there's no driving force for it to do anything. Nature doesn't like to go out of harmony. Nature likes to go in harmony, and we're already in harmony. Everybody's the same. Okay? So why would we talk about this? Well, we now know the Nernst equation that says not only can we have cell potentials that come from the standard reduction potentials, we can have cell potentials that come from differences in concentration. So what I'm going to go ahead and do is I'm going to change the concentration of one side of this thing. So instead of this guy being 1 molar copper 2 plus in a new color here, I'm going to make this guy 0.001 molar copper 2 plus. Does that change anything? Well, it doesn't change our standard reduction potential because our standard reduction potential says 0. It's the same thing on both sides at standard conditions. But we've now changed the conditions. We now have non-standard conditions, and that's when we pull out the Nernst equation. We say E cell equals E cell naught minus 0.0592 over n times the log of Q. We know in this case E cell is just 0, so this is going to be minus 0.0592 over n times the log of Q, but I still haven't really probably convinced you that this is useful yet. How do we get Q in this case? Well, let's think about what could happen in this situation and see whether maybe it will happen. So what we're going to do is we're going to write things in color here. We're going to use copper solid on the left. And on the right we have green, copper 2 plus. And that's going to go to copper solid in green and copper 2 plus on the left. Okay? So I wrote this kind of proposal about what might happen. I'm like saying, hey, maybe the copper on one side is going to oxidize and the copper on the other side is going to reduce. Let's find out what that does. Q is going to be copper 2 plus in orange over copper 2 plus in green, right? Orange is on the left, green is on the right here. The green one is still at standard conditions, so it's just the orange one that we have here, and so it's going to be 0.001 molar. However, we need to plug that into our Nernst equation. And so we get equals minus 0.0592 over 2 in this case, because we transferred 2 electrons for each one of these things, times the log of 0.0010. And if you do that, you get a value of 0.089 volts positive. That's a positive cell potential. That is a cell that wants to run. If you calculate K for that, it would actually be a fairly large K still. So that's a cell that wants to run. You took something that was like, I put the same thing on both sides, nothing's going to happen. You changed just the concentration. It's still copper on both sides, but you changed just the concentration, and all of a sudden we now have a galvanic cell that actually wants to run. Why does it want to run? Well, what we said just a minute ago is nature likes things to be in balance, and we unbalanced it. We lowered the concentration on one side, and nature's like, I got to fix that. I want to try to make these equal over time. Right? Just like heat. Heat equalizes over time. You get a hot object and a cold object. The heat flows from the hot object to the cold object till they're equal. It doesn't flow until the other one's now hotter than this one, right? It flows until they're equal. Same kind of thing here. This is going to flow until they are equal. So what happened is I had a low concentration of copper 2 plus over here. I had a high concentration of copper 2 plus over here. So nature was going to be like, I need to make more copper 2 plus on the left. That's how I knew to draw this one this way. Is nature wants to drive it in that direction. If I'd guessed wrong, I would have gotten a negative, I should write this better here. Would have gotten a negative Ecell, and I would have been like, wait, negative Ecell, that's not spontaneous. It just means I mixed it up. Okay, so that's a hint for yourself if you're solving one of these concentration cells, is what it's called. If you get a negative Ecell, you know you just probably mixed up what was happening. But nature wants to make those equal. So it's going to say, hey, I need to make more copper 2 plus on the right-hand side. And at the same time, I need to decrease the copper 2 plus on the right-hand side. So that's going to go from copper 2 plus to solid copper. And so that's how I was able to put that reaction together, is by thinking about it. Okay. So that's the interesting thing about these concentration cells. Standard reduction potential, 0, right? Nothing there. But once you change that concentration, there is now a driving force, and that driving force in an electrochemical reaction can be measured by a voltage. Pretty neat. Not a huge one, by the way, right? You're not going to be like powering tomorrow's cars by just making sure that you've got different concentrations on your cells. One quick question to check in before we're done with this video. True, false, or not enough information? Because concentration cells have an E naught of 0 volts, and the actual voltage depends on Q. The concentration of the species in the anode and the cathode half cells, we do not need to know the identity of those species, and we can calculate cell potentials from just knowing the concentrations. Is that true, false, or not enough information to answer? So I want you to just think about that, and then go. It's an interesting question, isn't it? Hopefully you were thinking about it for a while. And quite honestly, I wrote this question maybe a little while ago, and I didn't write down my answer in here. So I was sitting here trying to think about it too. Okay, so let's just kind of talk through it. Well, concentration cells have an E naught of 0 volts. And the actual voltage depends on Q, the concentration of the species in the anode and the cathode half cells. Do we need to know the identity of those species? Or do we just need to know the concentration? Do I need to know that it's 0.001 molar copper? Or can I just know that it's 0.001 molar, right? Because you've got your Q is just going to be dependent on the concentration in one side, the concentration on the other side, and this was what, the lower over the higher. Oh, so that seems maybe possibly reasonable. And then we just plug it into the Nernst equation. We know this is 0, so we don't have to worry about that. And we have Q there. Great. But what's missing? N. We need to know the number of moles of electrons that have transferred. In our copper case, it was 2. But what if we were doing something that only changed charge by 1? Then it would be 1. What if we did something that changed charge by 3? Then it would be 3. So we do need to know the identity of these species, or at the very least, how many electrons there are. So I'm going to call this false. We do need more information. Now, if you came up with C because you're like, don't have enough information, I could totally understand that, right? And if you missed the little play pause it point, don't worry, it's probably not going to be the thing that decides your grade at the end of the semester. If it is, just send me an email, be like, Professor Clements, there was that one question in electrochemistry, and it's ruining my grade. I'll fix it, okay? So, make sense? Right? You do need to know something about the identity of the species, because in order to put it into the Nernst equation, you've got to put that N there. All right. Thanks so much for listening. Have a wonderful day, and I hope this was useful.